This is the video for section 12.1, 12.2, and this is going to be a short video because we did most of the work, and essentially we're going to look at curves in space, but it's very similar to curves in the plane that we did in chapter 10. Alright, so we can see, if you look at the title of that section is function, vector valued function. Vector valued function. What does that mean? Well, if you remember, I can see a curve in the plane as a function from r to r squared. So t is the parameter, and for every value of the parameter, I get a point in the plane, so a vector, xt, y2. So it's a vector value, so the value you get, the output is a vector in R2. So you can do exactly the same thing for curves in space. So in space, the three-dimensional space is going to be a function from r to r cubed, and for every t, now associate a point xt, yt, zt, three coordinates, because it's three-dimensional space, okay? And it's good for most of the time to think of t as time, all right? And I'm going to use the notation of the book where this point in the plane, in the space, x, y, z, I'm going to use the vector r to designate that point. All right. Okay, so we already did some of that when we look at straight lines. So straight line is a curve. It's just a flat curve, if you wish. And so in that case, in that notation, what's the parameterization we saw? We said that rt, the position in time, is t times the direction we call w plus a reference point, right? So it's all the multiple of w starting from r0. So for example, if I pick the direction 1, 1, 1, my curve, my line as time goes by is just t times this direction, so all the multiple, and let's say I start from the origin. Okay, so we already saw this. So the difference here is that if you think about that, so what's my functions xt, yt, zt here is just t, right? So it's a linear function of t. So that's why it's straight. But maybe we can look at other function of t and get some more funky curves, all right? Okay? And another notion that is important, that's why I use the notation r here instead of v for vector, is that we have an interesting quantity called the velocity vector. The velocity vector is simply the change of position as t varies. But since the position is in three-dimensional space, right, then a change of position is also in three-dimensional space. So this velocity vector has three components. And so how do you do it? So we already did it in two-dimensional space. So in two-dimensional space, so in 2D, the velocity vector is simply the change in x and the change in y. Okay, so how do you change in the x direction with respect to t, and the same thing in y? It's the same thing here. So in that case, in this simple example of the line, the velocity is the vector 1, 1, 1's direction. So the velocity is constant in that case. Okay, so it's simple to actually take the derivative of the vector of the position, rt, you just do it coordinate by coordinate. Okay, so in that case, the velocity vector again is constant. The direction doesn't change, and that's going to be, it's not true in general, obviously. All right, so let's do an example that's slightly different. So I'm taking, this is actually the example of a spiral. So what's a spiral? Well, there's several spiral, but here's an example of one. So the position x is 4 cosine t. So at time 0, x equal to 4. Yt is 4 sine t, so at t equals 0, it's 0. And the z is simply t. Okay? So if you think about it for a second, let's say I don't have this z-coordinate. I just look at the xy. This is the equation of a circle of radius 4. Okay. So note that x squared plus y squared is equal to 16. Okay. So if I just look at how the point moves in the xy plane, it's a circle. Okay, like this. Radius 4. However, the difference is that I also change the z-coordinate, and it changes like t. So what happens is you draw that circle, but as you draw it, as time goes by, you go up. So it makes a spiral. So you draw that circle around the z-axis, okay, but you go up at the same time as t. Okay. So that's a spiral. Now you can compute the velocity vector. So again, coordinate by coordinate, you get minus 4 sine t for the x derivative, 4 cosine t for the derivative of yt, and 1 for the derivative of zt. Okay? Which makes sense because that means the velocity in t is constant as 1. So if I look at the change of coordinate in t, the speed is constant. Okay? But what's the speed in the xy coordinate? Well, let's say at t equals to 0, okay, I'm at x is equal to 4. And what happens there, so the point, the circle is going this way. And if you think about it, the velocity is actually tangent to the circle, okay, because it's the vector 0, 4, okay? So 0 in the x coordinate and 4 in the y coordinate, okay? And if you do it, let's say for t equals to pi over 2, okay, then what you're going to get is the velocity minus 4, which goes in the x direction. So the velocity is always tangent to the circle in the xy direction, okay? So you swirl around like this in the xy and you go up at the same time. Now you can also look at the acceleration vector, okay, which is the second derivative of the position or how the velocity changes with time. And again, you just take the derivative of each coordinate, right? And so you're going to get here minus 4 cosine t for x, minus 4 sine t for y, and 0 now for the z coordinate. Okay, so there's no change of speed in the z direction, which makes sense because the speed was constant. Okay, and if you think about this, where does the vector point? Well, if I look at t equals to 0, the acceleration vector will be minus 4, so it's like pointing towards the center. At t equals to pi over 2, I get minus 4 in the y direction. If you do every point, the acceleration is going towards the center. And if you remember some physics, if you've ever taken physics, that's the force, the centripetal force, okay, opposite to centrifugal force. Anywho, okay, the important point for us here is that you can take derivative of the position and you can take several derivatives. You just do it coordinate-wise. Okay, so it's the same calculus, you just have one more coordinate. And you can do the length exactly like curves in the plane. So remember, the length was just summing the Pythagoras theorem. So integrating the small triangle. Now I also have the height. So Pythagoras dx squared plus dy squared plus dz squared, square root. If I parameterize with respect to t, take the dt out, okay? So how does that look like? Well, if you think about that for a second, this is actually the size of the velocity vector that you're integrating, okay? And so let's say you want the length between 0 and 2 pi of the spiral. So the velocity vector was here. Okay, so you're going to get 16 sine square plus 16 cosine square, so I just get 16 plus 1. So this is going to be 16 plus 1, right, dt. So the length of the spiral between times 0 and 2 pi is 2 times square root of 17. All right, so again, this is not hard. Even though you're in 3D, it might be hard to visualize. The calculus is simple. Just do it coordinate by coordinate. Okay? Thank you for listening.